Hello, in this video I'd like to answer some questions about the expressiveness of WS1S, the weak monadic second-order theory of one successor. These are the sorts of questions that I'm interested in. Given a particular formal language, what sorts of things can we express in that language? In a previous video, I introduced the weak monadic second-order theory of one successor. It's a two-typed logic with lowercase variables representing natural numbers and uppercase variables representing finite sets of natural numbers. We then have the natural containment relation in between them, and we can also talk about the successor operation on the natural numbers, the +1 operation. And we also have all of the basic first-order logic stuff, quantifiers over both the first and second-order types, equality, both for first and second order types, and Boolean operations, and or not, whatever we need. In that video, I showed that we could express less than or equal to in that particular logic. In particular, there's some formula phi of x and y that holds if and only if x is less than or equal to y. And I also showed that we can express whether or not a number is even. There's some sort of predicate phi, such that phi of x holds if and only if x is even. These are sort of the easy questions of expressibility, showing that you can express something just by giving you the logical formula that expresses it. In that video, I also gave a complete classification of the things that we could express in weak S1S. If we translate natural numbers n to words of the form a to the n b, and sets of natural numbers to words that have b's in positions indexed by elements of those sets and a's everywhere else, then formulas in weak S1S correspond to regular languages, and thus to finite-state automata. In this video, I'd like to take advantage of the fact that we have all of these different perspectives on the regular languages in order to answer some intermediate questions of expressiveness. In particular, what sorts of things can we say about first-order elements in weak S1S? What sorts of things can we say about natural numbers? I'll start with the simplest question. What sorts of predicates phi of x, so some sort of formula that just takes in one first-order element, can we express in weak S1S? So for instance, this includes our predicate that tells us whether or not a number is even. Notice that in this formula here, I am making use of the second-order variables. They're just not free variables, right? They're quantified over. They're not things that the predicate is saying anything about. They're just inside of the formula. This would be a very different question if we were restricted to not be able to use second-order variables at all. As I showed in the weak S1S video, we can translate our formula phi into a corresponding automaton, a sub phi, that accepts exactly words of the form a to the nb, where n satisfies phi. So a to the nb is how we represent the number n as a word, and it's exactly the representations of the numbers that satisfy phi. So we're able to conclude that this here is some sort of regular language. The question is, what sorts of regular languages are there that are of this form? What sorts of regular languages consist exclusively of words of the form a to the nb for various n, but maybe not all n? This question will be much easier to answer if we can translate it into the question of asking, what can we say if we know that the set of all a to the n such that n satisfies some predicate phi is regular? And there's various ways of doing this. We could look at the state diagram for our automaton a sub phi, and whenever we see an edge coming out of a state labeled with a b leading directly to a final state, we get rid of that edge and leave the original state as an accept state. Another option is to look at a regular expression for this language here, and find a procedure for getting rid of the final b's from the regular expression to produce a regular expression for this language here. Another option is to use the word logic. Because we know that this set of words here is regular, there's some sort of predicate P in the word logic that's true exactly of words of this form. And then we can just construct a new predicate in the word logic Q that holds if and only if P holds of the successor B of W, that is W with a B tacked on to the end. And thus the set of words that satisfy Q is going to be this set here, and because this set corresponds to a predicate in the word logic, we know it must be regular. However you do it, there are lots of different ways of proving that this set here must be regular. In fact, one option is to simply go back to the proof where I showed that formulas in weak S1S correspond to automata, and instead of representing the number n as a to the nb, change up the representation so we were just representing the number n as a to the n. The proof works exactly the same way. You just have to change the encodings and it works perfectly fine. It's just that I like this encoding here because this encoding means that we're representing a natural number the same way that we represent the singleton set containing that natural number. And that turns out to be very nice. But however you do it, we're able to conclude that this set here is regular, and so what does that mean? What sorts of regular sets consist of just one character in their alphabet? This is actually a fun question to think about. I encourage you to pause the video and go through the different representations of regular languages that we've talked about and see what they have to say about this problem. It turns out that actually the best perspective on this question is to just look at the corresponding finite-state automaton. What does the state diagram of a finite-state automaton on an alphabet with a single character look like? Well, there's going to be some sort of start state, and then, well, the only thing we can do is read the character A, and that will possibly take us to a different state. And then when we're in that state, we can read the character A, and that'll take us to possibly a different state, and so on and so forth. And because this is a finite state automaton, eventually we're going to wrap around to a state that we've already been in. And this is it. This is what the state diagram has to look like for our finite state automaton. It has to look like some sort of path leading up to a loop. And the path could be empty. It could be the case that we loop all the way back around to the start state. But that's it. That's what our state diagram has to look like. The only thing that's missing is the except states. We have to pick some of these states to be except states. Let's pick some arbitrary number of them and see what happens. So when we read the empty word, when we read a to the 0th, we get to the start state, and that's an accept state. So we accept the empty word, we accept a to the 0th. If we read just one a, so a to the 1st, that takes us to this state here, so we also accept. If we read two a's, then we reject. If we read three a's, we accept. If we read four a's, we reject. If we read five a's, we reject. If we read six a's, we accept. If we read seven a's, we accept. 8 we reject. 9 we accept. 10 we accept. 11 we reject. 12 we accept. 13 we accept. And so on and so forth. And the pattern that we have here is that either n is one of these initial numbers, or n is greater than or equal to 5, and we've gone into this loop where we accept only if n is congruent to 6 or 7 mod 3. We call sets like this eventually periodic. That is, beyond some point, in this case beyond n is equal to 5, the behavior of the set is entirely periodic. Whether or not we have an element of the set depends just on its remainder modulo some period. But before that point, we can have arbitrary behavior. The phenomenon of eventual periodicity shows up all over the place in mathematics, and it'll show up later on in a completely different context later on in this video series. Perhaps the simplest instance of eventual periodicity is in the decimal digits of a rational number. They can be whatever we want up to a certain point, but beyond that point, they're just going to repeat forever. And if we construct a sequence that's b's in positions indexed by numbers in this set here, and a's everywhere else, this sequence has exactly the same sort of eventual periodicity as a rational number does. So we were able to conclude that given the assumption that phi was some sort of first-order predicate in weak S1S, that the set of all n such that phi of n holds is some sort of eventually periodic set, that phi was some sort of eventually periodic predicate. And we can actually run this proof in reverse to conclude that if we have some sort of eventually periodic predicate, that there is a corresponding formula phi in weak S1S that expresses it. But it's actually more enlightening to try to do this reversal directly. I encourage you to pause the video and take some sort of arbitrary eventually periodic set like this one and try to translate it into some sort of predicate in weak S1S. You'll want to adapt or maybe even make direct use of the formulas that we had for x is less than or equal to y and x is even. So what happens if we extend the question to ask about two first-order elements? What sorts of things can we say about pairs of natural numbers in weak S1S? Again, by our equivalence, we can translate our formula phi into an automaton a sub phi that accepts exactly the encodings of pairs that satisfy our formula phi. So how did we encode pairs of natural numbers as a single word? Suppose we wanted to encode the pair 7, 4. We first translate each of them individually into words. So 7's going to be this word, 7a's, followed by a b, and 4 is going to be 4a's, followed by a b. And then we're going to want to merge these words together so that we can read them in simultaneously in our automaton a sub phi. So first we pad out the shorter word to be the same length as the longer word. And then characters of the merged word are just going to be pairs, one from the first word, one from the second word, and I'll denote these pairs by vectors. The sorts of words that we get wind up depending a lot on which of x and y is larger. In particular, which of one of these two are we going to have to pad? Specifically, in each of these cases, we're going to wind up getting words that match one of these three regular expressions. And it's best to handle these cases separately. The case when x is less than y is exactly like the case where x is greater than y. The variables have just been switched. But actually, let's start with the case where x is equal to y. We can isolate this case specifically by taking the language that our automaton accepts. Let's call that language L, and intersecting it with this template here. When we do that, we're going to get a language that looks like this. Words that are some number of copies of A followed by a B, where that number of copies, x, satisfies phi of xx. And because the intersection of regular languages has to be regular, we know that this language has to be regular. And we have exactly the same question that we had before. What sorts of languages consist exclusively of words, some number of copies of one character followed by another character? So we can conclude that this set here has to be eventually periodic. What about the case where x is strictly greater than y? Again, we can take the language accepted by our automaton and intersect with this template here to focus in just on that case. When we take that intersection, we get exactly the set of words here, exactly the encodings of pairs x, y. Notice that there are xa's at the top and y's at the bottom. Exactly the encodings of pairs x, y that satisfy phi and have x strictly greater than y. And again, because the intersection of regular languages is regular, this language has to be regular, and so what can we conclude about phi from that? This is a bit of a harder question than before, but I found two approaches that seem to give a good picture of what this winds up looking like. The first is to try to construct a state diagram for the automaton that accepts this particular language. Now, drawing out our state diagram is going to get really messy really quickly. There's 4 characters that we care about in our alphabet, and you can imagine every single state we have an edge coming out corresponding to each of those characters. It's going to be quite a mess. So in order to keep things organized, I'm going to not draw any edges that don't have any futures. That is, that can't eventually lead to an accept state. So for instance, when we're looking at the start state, right, technically speaking, we're going to have edges coming out of this state for each one of our characters. But really, if we saw an A octothorpe or a B octothorpe in this state, we couldn't get a word of this form. And so let's not draw those edges for this particular state. Let's actually start out by just focusing on what happens if we're in the start state and we read some number of AAs. One AA is going to take us to potentially another state. I guess we could loop around immediately, but let's imagine that that doesn't happen. Because this is a finite state automaton, eventually when we read enough AAs, we'll wind up getting back into a state that we already were in before, giving us this familiar path and loop configuration for this part of the automaton. Once we've read all of our AAs, we then expect to read an AB. And let's actually say, for the sake of example, that if we read an AB in this state here, that there is no future, so I don't have to draw it. Once we've read our AB, we can expect to read some number of A octothorpes. And again, we're going to get that familiar path and loop configuration. Again, we'll eventually have read enough A octothorpes to take us back into a state that we already were in before. And of course, if we're in any of these states, we don't expect to read an AB or an AA, so again, I'm not drawing the edges corresponding to those characters coming out of these states. Once we've read all of our A octothorpes, we expect to read a B octothorpe. And by our convention, since I'm only drawing edges that have futures, these edges should lead to accept states. And these accept states in particular correspond to words of this form where there are 0 AAs, so y is equal to 0, followed by an AB, followed by either 1 A octothorpe or a number of A octothorpes that's larger than 2 and congruent to 3 mod 3, followed by a B octothorpe. And so we have conditional on the value of y on the number of AAs that x minus y minus 1 has to fall into some specific eventually periodic set. Now, if we're drawing our state diagram, it's entirely possible that this edge here, that if we're in this state and we read an AB, it can't take us to any of these states because that won't produce words of this form, but it could take us to one of these states, for instance. Let's say that it took us to this state here. If we allow that sort of thing in our diagram, it's going to make a huge mess. of arrows coming out of states here, going into states over here. In order to keep things organized, what I'm actually going to want to do is take this entire chunk of the automaton and duplicate all of the states and copy them down here. And it's not going to affect the behavior of the automaton. It's not going to accept its language. But it is going to allow us to see the underlying structure of this diagram, where this state leads to one region of the automaton, this state leads to another region of the automaton, this state leads to another region of the automaton, and so on and so forth. Keeps everything nice and separate so we can analyze it separately. So this accept state here corresponds to reading in the word AA, AB, B octothorpe. So there's one AA, y is equal to 1, and there's 0 A octothorpes, x minus y minus 1 is equal to 0. And then this accept state here corresponds to reading 1 AA, an AB, and then a number of A octothorpes congruent to 2 mod 3, and then finally a B octothorpe. So y equals 1 and x minus y minus 1 is congruent to 2 mod 3. Y is equal to 1 and x minus y minus 1 falls into a particular eventually periodic set. And then finally, if we make it to this state and then read an AB, let's say, in order to get to the accept state, we need to read at least one A octothorpe before reading our B octothorpe. And this is after reading a number of AAs that's greater than or equal to 2 and congruent to 2 mod 2. So this accept state here corresponds to y being congruent to 2 mod 2 and greater than or equal to 2, and then x minus y minus 1 being just at least 1. And so hopefully you can see that the automata that we get when we take languages like this and draw out their state diagrams, the automata that we get are piecewise on y. Each of the pieces is going to be, maybe it's just a single number, or maybe it's some eventually periodic set. And then depending on the piece, x minus y minus 1 has to fall into some eventually periodic set. So that tells us that the set of all pairs xy such that phi of xy and x is greater than y has to have that form. Again, piecewise on y, where the pieces are eventually periodic sets. Singletons are eventually periodic sets that are just periodically not there eventually. X minus y minus 1 has to fall within a particular eventually periodic set. And again, it's worthwhile taking some piecewise eventually periodic set like this and actually trying to convert it into a formula phi in weak S1S just to see how that translation's done. It's mostly just Boolean stuff. The tricky part is showing that we can express that x minus y minus 1 falls into some eventually periodic set in weak S1S, a language that notably doesn't have subtraction or addition in it. So we've already answered the question of what this set here must look like, but I think it's interesting to also look at it from the perspective of regular expressions. We know the set is regular, and so it has some sort of regular expression, and we can actually say a fair amount about what that regular expression has to look like. Since in this language, this character and this character only appear exactly once in every word, they actually can't be inside any Kleene stars, anywhere inside a Kleene star within the expression, because that opens up the possibility of that character showing up more than once. You can just kind of prove by induction on the construction of the regular expression that that always opens up the possibility of the character showing up more than once. And so these characters have to show up towards the outside of the regular expression. If we then apply the fact that concatenation distributes over union, A concatenated with B union C is equal to A concatenated with B unioned with A concatenated with C. I'm using this plus for union now. It's slightly nicer because this looks like distributivity. If you apply this and you apply right distributivity, you can wind up getting a regular expression that doesn't have any unions directly inside concatenations. And so if we take these two conditions, these two characters can't appear inside any Kleene stars, and there are no unions directly inside concatenations, there's really only a few possibilities for what the regular expression can look like. In particular, the regular expression is going to wind up having to look like some sort of union over concatenations of the form some regular expression that defines a language exactly over AA. The AA is the only character in that language, followed by an AB character, followed by a regular expression for a language that consists exclusively of A octothorpe characters, followed by the B octothorpe character. And again, the question of what sorts of regular languages are there over a single character, we answered that before. It's just numbers of copies of that character that fall into some eventually periodic set. So in particular, we're going to be taking a union over regular languages of this form, where the number of AAs falls into one eventually periodic set, and the number of A octothorpes falls into another eventually periodic set. In other words, the set of all xy, such that phi holds of xy and x is greater than y, has to be some union over sets where y falls into some eventually periodic set and x minus y minus 1 falls into another eventually periodic set. In other words, we can express phi of xy with x greater than y as some sort of Boolean combination of requirements, either that y be in some eventually periodic set or that x minus y minus 1 be in some eventually periodic set. And this is just another way of expressing the requirement that x minus y minus 1 falls into some eventually periodic set depending on which of a possible number of eventually periodic sets that y falls into. So we know that the set of all pairs x comma y satisfying phi, that's just going to be this union here. The union over the pairs where x is greater than y, the pairs where x is equal to y, and the pairs where x is less than y. And we know that this set here is some sort of Boolean combination of sets of pairs of the form x comma y, where y falls into one eventually periodic set and x minus y minus 1 falls into another eventually periodic set. This set here has to be exactly the set of all pairs xy, where x is equal to y and x falls into some eventually periodic set. And this case here is just the reversal of this case here. It's just going to be some Boolean combination of sets of pairs xy, where x falls into some eventually periodic set, and y minus x minus 1 falls into another eventually periodic set. So all in all, phi of xy is just going to be some Boolean combination of assertions about how x and y compare to each other, and assertions about x and y potentially falling into certain eventually periodic sets, and assertions about their difference falling into various eventually periodic sets. And that's it. Phi of xy has to be equivalent to some Boolean combination of these. So I hope you can see just how powerful it is to turn expressions in weak S1S, and this also applies for Büchi arithmetic or the word logic, to be able to turn those expressions into some sort of other expression of the regular languages, either a finite state automaton or a regular expression, or maybe a non-deterministic finite state automaton, or maybe a formula in a different logic that we had. And you can keep going. It's not that hard to extend this case to the 3-variable case or the 4-variable case and so on and so forth. You can see that really the only things that we can say about first-order elements in weak S1S are going to be Boolean combinations of some sort of comparison of the elements, assertions that the elements fall into eventually periodic sets, and assertions that differences of elements fall into eventually periodic sets. It's actually worth taking a moment to compare this to the Büchi arithmetic case. Weak S1S actually can't say that much about natural numbers, but it makes up for it in being able to talk about finite sets of natural numbers as well. Büchi arithmetic can talk exclusively about natural numbers, but it can actually say more. It's very easy to talk about these sorts of things, and of course this is a logic, so we can talk about Boolean combinations of these sorts of things in Büchi arithmetic. We actually only need addition. We don't need V2. And you can actually show that you can't talk about addition in weak S1S. We'll see that using kind of a proof by contradiction later on in this video series, but you can also just kind of use this logic here, show that addition can't be expressed as a Boolean combination of these sorts of things. So Büchi arithmetic can say way more about natural numbers than weak S1S can. But I don't think that's really a fair comparison, because natural numbers in weak S1S don't actually correspond to natural numbers in Büchi arithmetic. Natural numbers in weak S1S actually correspond to powers of 2, right? If you translate them into words and translate those words into the corresponding elements in Büchi arithmetic, it's going to look like powers of 2 in Büchi arithmetic. So really what we're asking when we translate this question from asking about weak S1S to asking about Büchi arithmetic is, what sorts of things can Büchi arithmetic say about powers of 2? And then it's just assertions like this on the exponents. So I hope that gave you an appreciation for how we can answer questions about expressibility in these various logics that wind up being equivalent to the regular languages. Please leave any questions or comments you might have below, and be kind to each other.